Welcome back. In the last few lectures, we discussed the performance aspects of individual components of a vapor compression refrigeration system. In this lecture, I shall discuss the analysis of a complete vapor compression refrigeration system. So, the specific objectives of this particular lecture are to introduce the concept of complete system analysis, discuss briefly the principles of graphical and mathematical methods, illustrate the concept with a simple example, and finally discuss briefly the importance of sensitivity analysis. At the end of the lecture, you should be able to explain the meaning of system analysis, explain the differences between graphical and mathematical methods, perform a simple analysis if component data are given, draw relevant conclusions from the results, and finally explain the concept of sensitivity analysis. Let me give a brief introduction. A complete basic vapor compression refrigeration system consists of, as you know, a compressor, a condenser, expansion device, and the evaporator. When assembled, the performance of each component is influenced by other components. That means they are interdependent when they are assembled in a system. A change in condition of one component affects performance of other components. Analysis of the entire system taking into account the characteristics of individual components is very much required to predict complete system performance and analyze the effects of external influence on system performance. A conventional method of complete system analysis is by using the concept of balance points. Balance points can be obtained either graphically or mathematically. In graphical method, the performance of two interdependent components is plotted for two same variables of common interest. Let me give an example. In fact, we have used this while discussing expansion devices. I am going to give the same example. The evaporator temperature versus mass flow rate is plotted for both compressor and expansion device at constant condenser temperature. The point of intersection of the two curves will indicate the conditions at which the mass flow rate and evaporator temperature will be same for the two components. This is the balance point for compressor and expansion device. So basically the graphical method we have discussed while discussing the performance aspects of, as I said, expansion devices. What we have done there is we have plotted the mass flow rate of compressor and mass flow rate of capillary tube versus the evaporator temperature. So we got two curves, one for compressor and one for the capillary tube, and the point where these two curves intersect is a point where the mass flow rate through the compressor is equal to the mass flow rate through the capillary tube. We call that point as a balance point, okay, because at that point the system is balanced, and the corresponding evaporator temperature is called as a evaporator temperature at the balance point, okay. So we have used this graphical method in case of compressor and capillary. Now the same method can be extended to other components also, for example condenser and compressor, condenser and capillary, capillary and evaporator, etc. Okay, so this kind of an analysis is known as graphical method of analyzing the system. Now in mathematical analysis, the performance characteristics of individual components are represented by mathematical equations. So as the name implies, you have equations for individual components, and the simultaneous solution of these equations gives the balance point. For example, in steady state, mass flow rate through expansion device and compressor are expressed as algebraic functions of evaporator and condenser temperatures. The balance point of the two components is obtained by simultaneous solution of the two algebraic equations. That means we have for example at a fixed condenser temperature, we have one curve for the mass flow rate of compressor as a function of the evaporator temperature. If you vary the condenser temperature, you get another curve, okay. Likewise, you can generate several curves for different condenser temperatures. Similarly, you can also generate the mass flow rate curves for capillary tube at different condenser temperatures and as a function of evaporator temperatures. So we can do the curve fitting for these curves, okay, by using a regression analysis, and we can get finally express the mass flow rate of a compressor and the mass flow rate of a capillary as an algebraic function of evaporator and condenser temperature. So in order to find the balance point, what we have to do is we have to simultaneously solve these two algebraic equations. Okay, so at balance point, as you know, the mass flow rate through compressor is equal to mass flow rate through the capillary. So that is the condition we have to apply to these two equations, and we have to find out the values of evaporator and condenser temperature at which this balance takes place. So that is the balance point, and this is the method of mathematical analysis. Okay. So the graphical method considers only two components at a time, for example compressor and capillary, okay, while the system analysis by mathematical means can consider more components simultaneously. Okay, this is the major difference between graphical method and mathematical method. A steady state system analysis will involve simultaneous solution of algebraic equations. So if you have a steady state system, all that you have to do is you have to solve a set of algebraic equations. Whereas a dynamic system analysis, that means an analysis where time comes into picture, okay, the performance variation again is time. This involves simultaneous solution of partial differential equations. So in this lecture we deal with steady state analysis of the system. That means we will be solving only algebraic equations. So balance points of condenser, compressor, evaporator combination will be considered for illustration. So I take a simple example, as I mentioned in the introduction. I will show the concept by using a very simple example. The performance data of industrial components is presented in the form of plots or equations. The raw data for this purpose can be obtained from the catalogs of manufacturers of various system components. Let me make one thing very clear here, that you require, in order to perform the complete system analysis, you have to have some raw data on individual components. For example, for the compressor, how the mass flow rate of an actual compressor, actual industrial compressor, how does it vary with evaporator temperature, how does it vary with condenser temperature, etc. Okay, so we have evaluated the mass flow rate, etc., using some kind of an idealized concept, and we have evaluated the volumetric efficiency and calculated the mass flow rate, etc. Okay, but in actual compressor there will be some other deviations which cannot be considered in a theoretical analysis. So the performance of actual compressors will be slightly different from the theoretical analysis. Okay, so normally for complete system analysis, it is better to take the values or the data supplied by the manufacturer, which is generated from the actual test conducted on the components. Okay, so from this actual test data on the components, you can fit equations or you can generate curves, and using these curves we can do the complete system analysis. Okay, so that is the procedure generally followed. So first let us look at the performance characteristics of reciprocating compressor. Basically in this example we are considering a reciprocating compressor, and the equation is generally holds good for a hermetic type of compressor. So for the purpose of balancing, what is done here is the refrigeration capacity is required as a function of evaporator and condenser temperature. So we what we do is we always take the refrigeration capacity as a required performance parameter. Okay, and express this in terms of the other individual parameters. So let me show the variation of refrigeration capacity with other individual parameters. In fact, we have seen this earlier. So this graph shows the performance of an industrial reciprocating compressor, and here capacity is plotted on y-axis, and on x-axis you have the evaporator temperature, and capacity is given for different condenser temperatures. Okay, you can see one thing that you can notice here is, for example, for a given condenser temperature, let us say a condenser temperature of 40 degrees centigrade, the capacity increases as the evaporator temperature increases. Okay, the same thing is also observed in case of a theoretical analysis also. That means an actual component, the trends will remain more or less same as that of a theoretical analysis, but the values will be slightly different. Okay, and you can also see here that at a given evaporator temperature, as the condenser temperature reduces, the capacity increases. Okay, so these aspects we have considered, we have already discussed while discussing the reciprocating compressor. So now you have three curves, okay, for three different condenser temperatures, and as a function of evaporator temperature. Now you can, for each of the curve, you can fit an equation. For example, let us say the QE is the capacity of the system. So QE can be expressed as a function of TE and TC. Okay. But generally it will be an algebraic equation, a polynomial equation, for example. So for this kind of a compressor, it is shown that you can represent the performance characteristics by this equation. Okay. And this equation involves 9 constants, and it also involves evaporator and condenser temperatures. So we have to, in order to find the constants, we have to know the data at, for example, 9 points. Okay, for example, let us say that I have so using this, let us say I take 3 points each for 3 different temperatures, condenser temperatures, and different evaporator temperatures. So we have a total of 9 points. Okay, and at these 9 points I know 9 values of capacity. Okay, so using these point data, we can then we can use this equation. Since you have 9 points, and in this equation we have 9 unknowns, these 9 unknowns are the 9 constants. So if you simultaneously solve these 9 equations, you can find out the constants A1 to A9. Okay. So as I said, the performance is represented by the equation QE is equal to A1 plus A2 TE plus A3 TE square plus A4 TC plus A5 TC square, like that. Okay, you have A6 TE TC, several terms. Okay, so there are 9 terms here and 9 constants. So in the above equation, TE and TC are evaporator and condenser temperatures, and AIs, as I said, are constants. The constants AI may be determined by curve fitting the data using least square method, or you can also do it by having a point on 9 point data and simultaneously solving the equations. Okay. Now let us look at the performance characteristic of a condenser. Representing the actual performance of condenser is quite complex, as it involves de-superheating, condensing, and subcooling zones. In fact, this point we have discussed while discussing the design of a condenser. In an actual condenser, you have 3 distinct zones. The first zone is where single phase heat transfer takes place, and the refrigerant vapor gets de-superheated by rejecting heat to an ambient. Okay, during that process, its temperature reduces. Then it enters into the 2-phase region where condensation takes place. So you have a phase change process. Okay, so you can also have, depending upon the operating conditions, a third zone where the refrigerant liquid undergoes subcooling. Okay, again this is a sensible heat transfer process. So you have 2 sensible heat transfer processes and 1 latent heat transfer process. And as you know, when you are using a pure refrigerant, the refrigerant temperature remains constant during the phase change process, that means during the condensation process, but its temperature varies during the de-superheating and subcooling reasons. So the actual analysis of a condenser, you must consider all these 3 zones. Okay, the temperature variation has to be considered, and you have to calculate the area required for the first zone, area required for the second zone, area required for the third zone, like that. Okay, this is what is done in the design of actual condensing equipment. Okay, but most of the time, for the sake of simplicity, what is done is we assume that the temperature of the refrigerant remains constant throughout the condenser, and throughout the condenser only condensation takes place. Okay, that means de-superheating and subcooling zones are also considered to be condensing zone. Okay, what is the advantage of making this kind of an analysis assumption? If you make this kind of an assumption, on the refrigerant side you have a single temperature. Okay, once you have a single temperature on the refrigerant side and a single heat transfer coefficient as that of the condensing heat transfer coefficient. Okay, so you on the refrigerant side, all that you have to do is find out the condensing heat transfer coefficient, and you know the condensing temperature. Okay, so this will considerably simplify the analysis, right? This is what is done here also. Okay, this is done, as I said, to simplify the problem, but remember that in an actual case the actual design will be slightly different because of the other 2 zones. Okay. So as I said, however, to simplify the procedure, it is assumed that total heat transfer from condenser can be found by treating it to be single region with condensation heat transfer coefficient. In fact, the justification for this was given while discussing the condensers. And temperature throughout the condenser is considered to be equal to condensing temperature. For air cooled condensers, the heat transfer rate can be written as QC is equal to UCAC into TC minus T infinity, where UC, as you know, is the overall heat transfer coefficient for the condenser, AC is the area of the condenser, and Tc is the condensing temperature, and T infinity is the ambient temperature. Okay, this is the equation which one can use for air cooled condensers. Whereas for water cooled condensers, one can use the equation like this: QC is equal to UCAC into LMTD, where LMTD is the log mean temperature difference. This in turn is equal to MW CPW into TWO minus TWI, where MW is the mass flow rate of the cooling water, CPW is the specific heat of the cooling water, TWO and TWI are the exit and inlet temperatures of the cooling water. Okay. Now, determination of balance point between condenser and other component requires that its characteristics be represented in the same form as done, for example, compressor. Okay, that is in terms of cooling capacity versus evaporator temperature. Okay, so for if you are using the balance point approach for complete system analysis, what we have to do is we have to express all the characteristics of the components in terms of common parameters. Okay, for example, if you take the refrigeration capacity as a required performance parameter, and if you want to express that in terms of the evaporator temperature, then all the component performance characteristics should be expressed in terms of refrigeration capacity and evaporator temperature. Okay. However, condenser by itself does not provide refrigeration capacity. Okay, condenser cannot provide refrigeration capacity alone. So one has to find the condensation rate of refrigerant in the condenser and then find the refrigeration capacity by multiplying it with refrigeration effect. That means what we do is first we find out QC, where QC is the okay, so first we have to find out QC. QC is the heat transfer rate in the condenser. From this QC we find out the mass flow rate of the refrigerant in the condenser, or the condensation rate. The condensation rate of the refrigerant is given by m dot subscript ref. This is nothing but QC divided by H2 minus H3, where H2 and H3 are inlet and exit enthalpies of the refrigerant. Okay, so if you know H2 and H3 and if you know QC, you can find out what is the mass flow rate of refrigerant through the condenser. Now under steady state, because that is what we are trying to do, we are trying to predict the performance under steady state, the mass flow rate through the condenser is same as the mass flow rate through the evaporator. Okay, so once you find out what is the mass flow rate through the condenser, this same mass will flow through the evaporator in the same time. Okay, so you also know the mass flow rate through the evaporator. So once you know the mass flow rate through the evaporator, we can find out what is the refrigerant capacity by multiplying the mass flow rate into the refrigeration effect. Okay, so that is what is done here. Finally we need the refrigeration capacity. QE is equal to m dot ref. This is nothing but the condensation rate in the condenser multiplied by H1 minus H4, where H1 minus H4 is the refrigeration effect. H1 and H4 are the exit and inlet enthalpies of the refrigerant. Okay, we are dividing this by 3.5167 because here all the refrigerant capacities are expressed in terms of tons of refrigeration. Okay, that is the reason why we are dividing in terms of 3.5167. Okay, so here the units of mass flow rate should be kg per second and units of enthalpy should be in kilojoule per kg. Okay. Now the characteristics of say a water cooled condenser can be obtained for fixed value of cooling water inlet temperature and flow rate. In this example I will consider only a water cooled condenser. Of course the same similar analysis can also be applied to an air cooled condenser also. Okay, so for the purpose of illustration we have considered a water cooled condenser here. So as I said, water cooled condenser characteristics can be obtained for fixed values of cooling water inlet temperature and flow rate. Okay. So let me show the graph first. So for example, this is the typical performance characteristics of a water cooled condenser at fixed cooling water inlet temperature and flow rate. Okay, that means here mass flow rate of cooling water and cooling water inlet temperature, these two are fixed. Okay, and here we plot refrigeration capacity in terms of evaporator temperature. Okay, one thing you can notice here is that at a given evaporator temperature, let us say some evaporator temperature, as the condenser temperature increases, the capacity increases. That means QE is increasing as Tc is increasing. Why Tc, as Tc increases, QE increases? Because we have fixed the mass flow rate of the cooling water, and we have also fixed the water inlet temperature. So when you are increasing the condenser temperature, then your log mean temperature difference increases. Okay, once log mean temperature difference increases, QC increases. Okay, once QC increases, mass flow rate of refrigerant increases. Okay, so this implies mass flow rate of refrigerant increases. Once mass flow rate of refrigerant increases, the capacity of the system increases. Okay, and you can also see here that for a given condenser temperature, for example, say 30 degrees centigrade, as the evaporator temperature is increasing, capacity is increasing. That means QE is increasing as TE is increasing. Why is it so? Because as TE increases, your heat rejection rate decreases. Okay, that means per ton of capacity, less heat has to be rejected in the condenser. Okay, if you have a fixed condenser, that means the area of the condenser is fixed. So if the heat rejected per ton of refrigeration reduces, means for a given condenser size, more capacity is possible, because the condensation rate will be higher. Okay, that is the reason why you get higher capacity. Okay. So it's as I said, it's observed that for a fixed evaporator temperature T, the capacity is higher at higher condenser temperature. A higher condenser temperature leads to a larger value of LMTD, which in turn gives a larger heat transfer rate and a larger condensate rate. And as I have already mentioned, at a fixed condenser temperature, the cooling capacity increases with increase in evaporator temperature due to reduction in heat rejection rate. This is due to higher condenser rate. This leads to higher condensate rate, which will give you higher capacity. Now the effect of entering water temperature on refrigeration capacity for various condenser temperatures can also be plotted. Okay, the last curve is for the fixed water inlet temperature and fixed flow rate. Okay, so we just varied the evaporator temperature and condenser temperature, and we got the capacity of the system. You can also study what is the effect of condenser water inlet temperature, that means the cooling water inlet temperature, on the capacity of the system. Okay, so if you plot this, you will find that it will be something like this. Okay, this curve shows on the x-axis you have the water inlet temperatures, on the y-axis you have the capacity of the system, and the capacity is plotted for different condenser temperatures. Okay, and here the capacity is 0, it starts with 0. Okay, the origin is 0. One thing immediately you can notice here is that when the cooling water inlet temperature is same as the condenser temperature, capacity becomes 0. Okay, that means when Tc is equal to T water inlet temperature, QE is equal to 0. This is obviously equal to 0 because once the cooling water temperature is same as the condenser temperature, no heat rejection can take place from the condenser. Okay, since no heat rejection can take place, there will be no condensation. Okay, once there is no condensation, there won't be any liquid mass flow rate, right? As a result, there won't be any refrigeration capacity. Okay, that is the first observation. Second observation is that for a given condenser temperature, for example, same 25 degrees centigrade, as the water inlet temperature reduces, capacity increases. Okay, that means as TWI reduces, QE increases. Again, the reason is similar. As the TWI reduces, for a given condenser temperature, your LMTD increases, so heat transfer rate in the condenser increases, that means condensation rate increases. Condensation rate increases means mass flow rate increases, mass flow rate increases means capacity increases. Okay. Similarly, at a given water inlet temperature, as the condenser temperature increases, capacity increases. Again, the reason is same. Once the condenser temperature increases, for a fixed water inlet temperature, LMTD increases, heat transfer rate increases, hence capacity increases. You can see that here the curves are almost straight lines, okay, and the slope, they are almost parallel to each other, okay, for different condenser temperature curves. So as I mentioned, the cooling capacity is 0 when the entering water temperature is equal to condenser temperature. As the inlet water temperature increases, for a fixed condenser temperature, the LMTD decreases, which decreases the capacity. The characteristics are straight lines with almost same slope for all the condenser temperatures. The condenser characteristics can be represented by the following algebraic equations. Okay, just like your compressor, you can also represent the condenser characteristics by an algebraic equation. First, at constant inlet temperature and flow rate of cooling water, you can get an equation like this, a polynomial equation QE in terms of evaporator temperature TE and condenser temperature TC. Again, this equation has 9 terms, so you have 9 constants B1 to B9. Okay, so again you have to use method of least squares, or you can also have 9-point data and solve the equation to obtain the constants B1 to B9. And in terms of cooling water inlet temperature, you can also write QE is equal to G into Tc minus Twi, where Tc is the condenser temperature, Twi is the water inlet temperature, and G is a proportionality factor. Its units are kilowatt per Kelvin or ton per Kelvin, and the value of Z depends upon the condenser design, and it can be obtained from manufacturer's catalogs. Okay. Now let us look at the performance characteristics of the evaporator. A refrigerant evaporator is also a heat exchanger, just you know that it is like a heat exchanger just like a condenser. Here the evaporator is considered to be a brine chiller. Okay. So what we have considered in this particular example is that evaporator is a brine chiller. Brine chiller means on the external fluid side you have a brine flowing. Okay. So refrigerant extract heat from the brine. Brine, as you know, is a solution of water and a salt, and normally brines are used where the required temperatures are lower than 0 degree centigrade. If you use the pure water, it will freeze, right, once the evaporator temperature falls below 0 degree centigrade. So when you want refrigeration at sub-zero temperatures, one can use brines. Okay. So the evaporator we have considered here is a brine chiller. That means you send the brine to the evaporator, brine gives heat to the refrigerant and it gets chilled. Okay. So what you get out of the brine chiller is a chilled brine, right. The cooling capacity of brine chiller can be represented in terms of brine flow rate and LMTD. For example, if you take a commercial brine chiller, you can get this kind of capacity curves. These are performance characteristics of a brine chiller as a function of brine flow rate and LMTD. Okay, they should be flow rate. So as the brine flow rate increases, you can see that the capacity increases for a given LMTD. Okay, that means capacity QE increases as flow rate increases. Why the capacity increases? Because as the flow rate increases, heat transfer coefficient on the brine side increases. Okay, H brine increases as the flow rate increases. Once H brine increases, overall heat transfer coefficient of the evaporator increases. Okay, once overall heat transfer coefficient increases, since you are keeping the LMTD constant, obviously your QE increases, because QE is equal to UE AE into LMTD, right, for the brine chiller. LMTD is constant, AE is constant, UE is increasing, so obviously capacity increases, right. Similarly, using this equation, it can be very easily shown that at a given brine flow rate, as the LMTD increases, the capacity increases. Okay, so this is easy to understand. So, okay, as I said, at a given LMTD, the cooling capacity increases with brine flow rate due to increase in brine side heat transfer coefficient, which in turn increases the overall heat transfer coefficient. Using these curves, one can find the cooling capacity at various brine inlet temperatures. Okay, how do you find that? For a given brine inlet temperature and flow rate, choose an appropriate LMTD. Okay, so let me explain with the help of the curves. Let us say that we know the flow rate. Okay, let's say that this is the flow rate, and you choose some LMTD. Okay, so let's say that we have chosen an LMTD of 4 degree centigrade, and this is the brine flow rate. And if the brine inlet temperature is also known, let us say that T brine inlet temperature is known. This is the brine inlet temperature. This is known to us. Then you can write from the energy balance. You can write QE is equal to mass flow rate of the brine into Cp of the brine into brine inlet temperature minus brine outlet temperature. Okay. So since you are you know the flow rate, okay, m dot b is known and LMTD is known, so you can find out QE, right. So QE is known to you, and m dot b is known to you. CPB can be obtained from the property data. TBI is fixed, so you can find out TBO. Okay. So first you can find out what is the outlet temperature of the brine. Once you know the inlet and outlet temperatures and you also know the LMTD, so from LMTD, brine inlet temperature and brine outlet temperature, we can find out what is the evaporator temperature. Okay, that is what is done here. So as I said, for a given brine inlet temperature and flow rate, choose an appropriate LMTD. Then from LMTD and flow rate, find the capacity using the characteristic curves, and find the brine outlet temperature using the equation QE is MB CPB into TBI minus TBO. From inlet and outlet temperatures and LMTD, find evaporator temperature. Okay, and as you know, for this brine chiller, the expression for LMTD is like this, where TBI is known to us, TBO is computed, T has to be obtained. Okay, so this is known to us. So there is only one unknown, so you can find out what is the evaporator temperature. So thus, a capacity versus evaporator temperature plot can be obtained for various brine inlet temperatures and fixed brine flow rate. Okay, so in this manner, what we can do is you can keep the brine flow rate fixed and then take another brine inlet temperature. Okay, once you take another brine inlet temperature, you get again different evaporator temperature. Okay, so likewise you can generate a data where you can express the evaporator temperature in terms of the the evaporator capacity in terms of the evaporator temperatures and brine inlet temperatures. Okay, so if you plot this, you will get this kind of curve. This is capacity versus evaporator temperature for different brine inlet temperatures, okay, and evaporator temperature at a fixed brine flow rate. Okay, so brine flow rate is fixed, right. Again, if you look at the characteristics, one thing that is immediately you can notice here is that when the brine inlet temperature, for example 5 degree centigrade, is equal to the evaporator temperature, then the capacity becomes 0. Okay, that means when TE is equal to TBI, QE is equal to 0. This is obviously the case because there is no temperature difference between the brine and the evaporator, so there cannot be any heat transfer. Okay, once there is no heat transfer from the brine to the refrigerant, the capacity will be 0. Okay, and what happens when the evaporator temperature reduces for a given brine inlet temperature? Obviously, as the evaporator temperature reduces for a given brine inlet temperature, your temperature difference between the brine and evaporator increases, so the capacity increases. Okay, so that is what is shown here. So as you move in this direction, capacity increases as the evaporator temperature reduces for a given brine inlet temperature. Similarly, at a given for example at a given evaporator temperature, as the brine inlet temperature increases, temperature difference between brine and refrigerant increases, so capacity increases. Okay, so these are, you can easily observe from these curves. One thing is, since we have fixed the brine flow rate constant, the brine side heat transfer coefficient remains almost constant. Okay, because the flow rate is fixed and the evaporator is fixed, means velocities, diameters, velocities, etc. are fixed. So the heat transfer coefficient remains more or less constant. If there is any slight variation, that may be because of the temperature variation, which is normally negligible. Okay. However, evaporation heat transfer coefficient increases with evaporator temperature. Okay. As a result, the capacity can be expressed as this equation, QE is equal to C naught into TBI minus TE plus C1 into TBI minus TE whole square. Okay. Again, here TBI and TE are brine inlet and evaporator temperatures, and C naught and C1 are constants which have to be obtained either from the regression analysis, either from least square method or from the point data. Okay, 2-point data. Now, the last component is the expansion valve. The flow characteristics of expansion valve play an important role in deciding the conditions achieved by the refrigerant system. However, what we do is, for simplicity's sake, here we assume that the expansion valve is capable of providing sufficient mass flow rate at all condenser and evaporator temperatures. Okay. You can also bring in the expansion valve into the analysis, and you can again have see what is the effect of the variation on the system performance. Okay. That means you will have to basically simulate the 4 component system performance. Okay. But for simplicity, what we assume here is that we have an ideal expansion device which will always provide the required flow rate at different evaporator and condenser temperatures. Okay, that means it will satisfy our requirement under all conditions. Okay. Now let us do the balancing of components. Okay, first let us do the balancing of compressor and condenser. Okay, this is known as a condensing unit. The combination of compressor and condenser is called as condensing unit. This unit draws refrigerant from the evaporator, compresses it, condenses it into liquid refrigerant, which is then fed to the expansion valve. The condensing unit is available as a packaged unit with matched set of compressor, compressor motor and condenser along with reservoir and controls. This may be air cooled or water cooled unit, which may be installed as an outdoor unit. Okay. So, this as you can see that a combination of compressor and condenser along with controls and the motor is called as a condensing unit. Okay. The condensing units are generally available off the shelf as packaged units. Okay. That means if you want a condensing unit for let us say a 10-ton system, okay, it is available off the shelf. You do not have to buy individual components and assemble them. Okay. So, you can buy it and then you can assemble the rest of the components, right, and these condensing units will be balanced by the manufacturer himself. Okay. He will do the balancing himself. So, the performance of condensing unit as function of evaporator temperature is obtained by combining the characteristics of compressor and condenser. Temperature and flow rate of entering water to condenser are kept constant. Okay. So, here what we are assuming is the inlet water temperature and the flow rate of cooling water both are constant, and matching is obtained by superimposing compressor performance on condenser performance. Okay. Let me show this. So, we had in fact we have seen this. This is the I have just discussed. These are the characteristics of compressor. Okay, compressor characteristics. Right, and this is the characteristics of the condenser. Okay. One thing you should notice here is here in both x and y axis have to be same for both the units. Okay. So, that is what is done here. Here for example, for compressor the y axis is capacity and x axis is evaporator temperature, and for the condensing condenser also the y axis has to be capacity and the x axis has to be evaporator temperature. Okay, both have got to be same and the scales also have got to be same. For example, if the evaporator temperature in this case is varying from let us say minus 10 degree centigrade to plus 10 degree centigrade, here also it should vary from minus 10 degree centigrade plus 10 degree centigrade. Okay, it has to be exactly same axis. Similarly, the capacity. Okay. Then the matching between the condenser and compressor is obtained by simply superimposing this onto this. Okay. So, if you superimpose that, you will get this curve. Okay. You can see here that what we have simply done is we have superimposed the compressor characteristics, okay, the black line onto the condenser characteristic curves, that is the dashed blue lines. Okay. So, these are superimposed. As I said, when you are superimposing them, the axes have got to be same, right. And how do you find the balance point? We find the balance point from the points of intersection. Okay. So, if you remember for the compressor, this is 30 degree centigrade, this is 35 degree centigrade. This is just an example. Okay. It can be any temperature, but 30, 35 and 40 degree centigrade. Okay. And for the condenser, this is 30 degree centigrade, this is 35 degree centigrade and this is 40 degree centigrade. Remember that here we are keeping the flow rate and cooling water temperature, inlet temperature constant. Now, what are the balance points here? The balance points are nothing but the points of intersection. That means you take the condenser line, for example, a 40 degree condenser line. Okay. Where the condenser line at 40 degree condenser temperature is intersecting with the compressor line at 40 degree condenser temperature. Okay. That is the balance point for 40 degrees. Okay. That is this point, right. So, at this point the 40 degree condensing temperature lines of compressor and condenser are intersecting. So, you get one balance point here, and at this point the compressor and condenser characteristic curves at 35 degree condensing temperature are intersecting. Okay. Similarly, at this point 30 degree centigrade condenser temperature balance point. Okay. So, if you join all these 3 points, you get the balance line, okay, or the characteristic curve for the condensing unit, right. And remember that this is at fixed compressor speed, fixed condenser water flow rate, and fixed condenser water inlet temperature, okay. And this red line is your balance or characteristic curve for the particular condensing unit, okay. So, that is how we have done the matching between the condenser and the compressor. In fact, you can notice here that this principle is exactly same as what we have done in case of compressor and capillary tube, okay. So, we have taken the x and y axis to be same for both the components, and then we have superimposed one graph on the other, and then from the points of intersection we could get the balance points. Same concept is applied here also, right. So, from the balance line it is observed that as evaporator temperature increases, the condensing temperature and capacity also increase. So, that you can see here. So, from this red line, that is the balance line, this line, you can see that as the evaporator temperature increases, the capacity increases, okay. At the same time, as the evaporator temperature increases, the balance condenser temperature also increases, okay, and we know the reasons why this happens. The variation of refrigeration capacity of the condensing unit with a variation in inlet water temperature of the condenser is obtained by superimposing compressor characteristics on the variation of condenser performance with inlet water temperature, okay. So, you can also find what is the effect of the condenser water inlet temperature, okay. This is done by again the principle of superimposing. For example, here this is what is done here. This picture shows the performance of condensing unit as a function of water inlet temperature, okay. So, this, as you know, is the characteristics of the compressor, okay. We have discussed before for the 3 different condenser temperatures of 30 degrees, 35 degrees and 40 degrees centigrade, okay. And this also we have discussed, this is the characteristics of the condenser as a function of water entering temperature, okay, for different condenser temperatures, right. Now, how do you get the characteristic curve here? For example, you choose an evaporator temperature here, right, then you draw a vertical line. Let us say that your condenser temperature is 40 degrees, okay. So, this vertical line intersects the 40 degree line at this point. So, from this point you draw a horizontal line where this line intersects the I am sorry, this should have been 40 degree, okay. Okay, so where this line intersects the 40 degree temperature line, that is this line, that will give you the balance point for the 40 degree centigrade line. Similarly, this point is for the 35 degree condenser temperature line, where if you draw a horizontal line where it intersects this 35 degree line, that will give you the another balance point. Similarly, for 30 degree temperature line, you can draw a horizontal line, and at this point this line intersects the 30 degree condensing temperature line in terms of cooling water inlet temperatures, okay. So, you can get very useful information from this one. For example, let us say that you know this one, okay, and you also know the condensing temperature. The first information that you can get is what is the capacity, right. Second thing is what should be the required water inlet temperature, okay. For example, for 40 degree centigrade, this has to be the condenser water inlet temperature, and for 35 degree centigrade, this has to be the condenser water inlet temperature. Similarly, for 30 degree centigrade, this has to be the condenser water inlet temperature. You can also do it in a reverse manner if you know this one, okay. If you want to find out what is the balanced evaporator temperature, that also can be done. You have to draw a line from here, okay, then come this side, and where the intersection is coming, go down and find the evaporator temperature, okay. So, that's how you can find out when one parameter is known, the other balanced other parameter at balance point. Okay, so as I said, line DEF is the characteristics of the condensing unit at evaporator temperature TE. It is observed that the cooling capacity decreases as the inlet water temperature to condenser increases. Obviously, as the inlet water temperature to condenser increases, for a fixed condenser temperature, the LMTD reduces. Once the LMTD reduces, the condensation rate reduces. Once the condensation rate reduces, refrigeration capacity reduces, okay. So, one thing you can notice here is by having the individual capacity curves, and by matching them we could get this kind of useful information. Okay, what happens when one parameter is changing, what happens to the other parameter, or what happens to the overall system performance. Okay, so that is the whole purpose of doing the complete system analysis. Okay. Now these characteristics can also be obtained mathematically by simultaneous solution of characteristic equations for compressor and condenser for constant inlet water temperature and mass flow rate. So far we have used the graphical method for obtaining the balance points, okay, between the compressor and the condenser, that means for the condensing unit. The same balance point can also be obtained if you know the characteristic equations for the compressor and the condenser. Okay, how can you do that? For example, we have for the compressor this equation, right? This is the equation for the compressor where you have 9 constants and capacity is expressed in terms of evaporator and condenser temperature. Similarly, for the condenser you have another equation which also consists of 9 constants B1 to B9. Here you have A1 to A9 and here you have B1 to B9 and evaporator and condenser temperatures. Okay, so suppose we have these equations. Okay, you can get this equation from the compressor characteristics and you can get this equation from the condenser characteristics. Okay, once you know the characteristics you also know the constants. Okay, once you know the constants, how do you find the balance point? We use what is known as the method of successive substitution to solve these nonlinear equations. First, what we do is for a given evaporator temperature we use a trial value of condenser temperature. And then using the compressor characteristic curve, for example, from the given evaporator temperature and the trial value of Tc, we can find out what is the capacity. Then what we do is we use this capacity and the evaporator temperature to find the condenser temperature from the condenser characteristic equation. Okay, and then we compare this calculated value of condenser temperature with the guess value of condenser temperature. If they are not same, then we change the we go for the second trial and we go on doing this iteration till we get the converse values. Okay, so this is the principle of successive substitution. Okay. Now let us look at the performance of complete system, that means condensing unit and evaporator. In steady state, a balanced condition must prevail between the condensing unit and evaporator. This is of course assuming that the expansion device provides the required refrigeration flow rate, and this is the assumption under which we are working out this example. This condition represents the performance of the complete system. This is obtained by superimposing condensing unit characteristics on evaporator characteristics for fixed cooling water inlet temperature and flow rate. Okay. So just like we have done for the compressor and the condenser, here again we superimpose the performance characteristics of the condensing unit. Okay, because we are trying to find the performance of the entire system. Okay, so we take the condensing unit characteristics and we superimpose this curve onto the evaporator characteristic curve. Okay, this is the evaporator characteristic curve. Remember that this condensing unit characteristic curve we obtained by superimposing the condenser lines and the evaporator characteristic lines. Okay, now what we do is we superimpose this onto this, right, and remember that this is at fixed compressor speed, fixed condenser water flow rate and condenser water inlet temperature, whereas the evaporator temperature is for the fixed brine flow rate and different brine inlet temperatures. So if you superimpose this, you get a curve of this kind. Okay, this I have shown for a one particular brine inlet temperature, that is of 10 degree centigrade. Okay, and this is the condensing unit characteristic curve, which what we have seen from the earlier this thing. That means this red line. Okay, because as I said, this is the curve for the condensing unit. So this curve is superimposed onto this one. Okay. And where these two curves intersect, that is this point, this will give the balance point for the entire system. Okay, and at this point you will find that the evaporator temperature is this. So this is the balanced temperature of evaporator. Okay. And suppose if the brine inlet temperature is not 10 degrees, but if it is 15 degrees, then you will have the curve like this, because the 15-degree curve is here. If it is 5 degrees, you will have another curve like this. Okay, so you can have different brine inlet temperatures, and again you can get the different balance points. From the performance curve, one can study the response of the system in transient state also. Okay. For example, as I said, this is a balanced point, and at this balance point, let us say that TA is the evaporator temperature at balance point. Okay, and let us say that due to some reason now system is in a transient state, and at this transient state, this is the evaporator temperature. Okay, so to start with, let us say that we have evaporator temperature TEC is equal to TB. Now there is no balance between condensing unit and evaporator, because you can see that the condensing unit, the capacity is this, whereas the evaporator, the capacity is this. Okay, that means the condensing unit has much higher capacity compared to the evaporator. Okay, and the difference between these two is the excess capacity. Okay, so when the condenser has an excess capacity, what happens? When the condenser has excess capacity, since the size of the condenser is fixed, it can condense more mass flow rate, or what it can do is, if for the given mass flow rate, the condensation can take place at lower condenser temperatures. Okay, that means your condenser temperature Tc will be reduced. Okay, once Tc reduces, when the condenser temperature reduces, evaporator temperature also reduces. Okay, once evaporator temperature reduces, the balance point will shift now from the unsteady value of TC to the steady value of TB. Okay, that means to start with, it is at this point, because of the excess capacity, condenser temperature reduces. Once the condenser temperature reduces, evaporator temperature also reduces. So the point moves in this direction. Okay, and when it reaches this point, both the capacities are matched, and the system reaches a steady state. Okay, so this kind of very useful information can be obtained by this performance characteristics curve for the complete system. Okay, so this is what is I have already mentioned. The condensing unit has higher capacity compared to the evaporator in transient state when the evaporator temperature is high. The excess capacity of the condenser leads to lower condensing and hence lower evaporator temperature, and finally balance will be restored to point A. The effect of brine flow rate can also be obtained from the graphical analysis. Okay, what happened? Let us say that this is the design flow rate. Okay, so this curve is for the design flow rate. Now the flow rate increases. Okay, let us say that this is the increased flow rate curve. Okay, what happens to the capacity? Once the brine flow rate increases, when you are keeping all other parameters constant and increasing the brine flow rate, the heat transfer coefficient on the brine side increases, because you are increasing the flow rate means you are increasing the velocity. So heat transfer coefficient increases. Once the heat transfer coefficient increases, overall heat transfer coefficient increases. Once overall heat transfer coefficient increases, capacity of the system increases. Okay, now the system will be balanced at a higher capacity, right? So that is what has happened here. So when you have increased the capacity, you can find that at this is the balanced design point capacity, and at increased brine flow rate, this is the capacity. Okay, but along with the capacity, the temperature also increased. Okay, if this is the design temperature, since the brine flow rate has increased, the balanced evaporator temperature also increased. Okay, you can also see the opposing effect. For example, when you are reducing the brine flow rate. Okay, this is the curve for reduced brine flow rate. When you reduce the brine flow rate, heat transfer coefficient on the brine side increases, overall heat transfer coefficient increases, evaporator temperature increases, capacity also increases. Okay, capacity also decreases. I am sorry. When the flow rate decreases, by evaporator temperature decreases and capacity also decreases compared to the design point. This is the design point. This is at the reduced flow rate. Okay, and at this flow rate, it is said that the evaporator is said to be starving. Okay, so that means evaporator is in starving condition when the flow rate is reduced. Okay. So that's what is summarized here. The results show that at higher brine flow rates, the heat transfer coefficient on brine side increases, which in turn increases the capacity. The evaporator operates at higher temperature. And at lower brine flow rate, the brine heat transfer coefficient decreases, which in turn decreases the capacity. The evaporator operates at lower temperature, and you call that state as a state of starving. An important aspect when you are doing the complete system analysis is what is known as a sensitivity analysis. What is sensitivity analysis and what is its use? This analysis is useful in the design and optimization of the system, and what does it tell us? It tells us what is the relative effect of each component on overall system performance. Okay. This kind of an analysis is called as sensitivity analysis. The mathematical simulation can be used to obtain this information. Okay. I will give an example. This is taken from the book of Stoiker and Jones. This gives a sensitivity analysis of a vapor compression system at a fixed condenser and fixed evaporator and ambient temperatures. What is done here is, this is the base case, okay, where you have a compressor. Let us say that the compressor capacity is 1 and you have a condenser capacity is 1 and evaporator has a capacity of 1. So, this is the base case. Okay. At this base case, it is observed from the calculation that the refrigerant capacity is 95.6 tons of 6 tons. Okay. Now, what is done here is all other parameters are kept constant. That means the condenser is kept constant. Now, no change is made in the condenser, no change is made in the evaporator. Only the compressor capacity is increased by 10%. Okay. That means it becomes from 1 to 1.1. When the compressor capacity is increased by 10%, you find that refrigerant capacity of the overall refrigerant capacity. Okay. So, this is the total system. Okay. Total system capacity increases by 6.3%. Okay. Now, in the second step, what is done is compressor is kept same, evaporator is kept same, but the condenser capacity is increased by 10%. When the condenser capacity is increased by 10%, you find that the total system capacity increases by only 1.3%. Okay. Next, the effect of evaporator is studied by keeping compressor and condenser constant, but by increasing the evaporator capacity, okay, by 10%. When you increase the evaporator capacity by 10%, you find that the refrigerant capacity increases by 2.1%. Okay. Now, when you increase everything by 10%, obviously the total capacity also increases by 10%. Okay. So, this is this kind of information you can get from the sensitivity analysis. What is the use of this kind of information or this kind of data? This data clearly shows that if you have to invest money, it is better that you invest money on the compressor, because a 10% variation in compressor is giving rise to 6.3% increase in the total capacity of the system, whereas a 10% rise in the condenser is giving only a 1.3% increase in the capacity. Okay. That means in terms of relative influence, compressor has the most influence. Okay. Next to compressor, evaporator has the highest influence. Next to that, condenser has the highest influence. Okay. So, you know where to do the improvement or where to invest, so that you can get the maximum possible benefit. This is the advantage of sensitivity analysis. Okay. Of course, the sensitivity analysis of an actual system can be quite complicated, because an actual system consists of several other components and several other factors have got to be considered. Okay. But this example just shows the basic concept and basic use of this kind of an analysis. Okay. This data along with the cost data of individual components can be used for cost optimization of the system. Okay. So, this is very useful. So, with this I complete the analysis of the complete vapor compression system. As once again, let me repeat that whatever we have discussed today is very brief, and it is only just to give an idea of how a system analysis, complete system analysis is done by using either a graphical method or mathematical methods. Okay. You can refer to more advanced books or journals for more information on this kind of system analysis. Okay. Let me summarize what we have learned in this lesson. In this lecture, a brief introduction is given on analysis of complete vapor compression system. Principles of graphical and mathematical methods are discussed briefly, and the concept is illustrated with a simple example taking a water cooled condenser and a brine chiller. Okay. So, at this point I stop this lecture. Thank you.